In this video, first we'll see how to write the gate-level Verilog design code for the full adder logic circuit. Then we'll learn how to implement a 4-bit adder by cascading full adders and write the Verilog code for that module as well. After that, we'll write the simulation code to see if our design is working properly. Using Vivado Design Suite, we'll do the synthesis, simulation, and implementation using the Verilog codes. At the final stage, we'll implement this design on a BASYS3 FPGA board by modifying the XTC file and generating the bitstream. First, we'll write the gate-level Verilog design code for the full adder logic circuit. You can see that in the diagram, inputs are shown in red, wires are shown in yellow, and outputs are shown in blue color. Now let's examine the Verilog code. You can see that we are defining our module with the name full add, and we are giving a list of ports, some carry out, AB, and carry in. Then we are defining which ones are output and which ones are input. We know from the diagram that sum and carry out are outputs. Here we define them. And then we say that AB and carry in are inputs. And after that, we define our wires, which are S1, C1, and C2. Then we are going to be defining the 5 logic gates that are in our circuit. So first we have our XOR here, this one, which is defined as AB inputs and S1 output. Then we have our AND logic gate, which is defined as C1 output, A and B inputs. Our second XOR here is defined as the output as sum and inputs are S1 and carry in. And the second AND gate that we have here is defined as output C2, inputs S1 and carry input. And finally, this OR gate is defined as the output is carry out and the inputs are C2 and C1. And after that, we close our module with the AND module command. Here we'll understand how a 4-bit addition is done. We will be adding 2 binary numbers. First number is 1011 and our second number is 0011. And this means that in decimals, this one is 11 and this one is 3. By using this table, let's understand how this 4-bit addition is done. Here you can see the inputs that we have, the carries, number A and number B, and here we have the 2 outputs, which is the sum and the output carry. Initially our input carry is 0, so if we add these 3 numbers 0, 1 and 1, our result is going to be 1, 0, so we are going to be writing 0 here and we are going to write our carry right here. So this carry as an output carry is going to be given as an input carry to the C1. So we will have 1 here. So in the second step, we are going to add these 3 numbers, which are 1, 1, and 1. So our sum is going to be 1, and our carry will be also 1. So this carry will again be an input here, and we will be adding these 3 numbers, 1, 0, 0. So this will be 1, and our carry will be 0. And let's send this carry to the input carry here. So we will have 0, 1, 0 added together. So this will be 1 and our output carry, which is our final output carry, will be 0. Now let's see this in a diagram to understand better. Here you can see that initially our carry input is 0. So we can write it here. And A0 and B0 can be seen here. So we are going to write 1 and 1 here. And our sum is 0 and our carry is 1. In the second step, we have again both ones for A and B, 1 and 1 here. So the sum is 1 and also the carry output is 1. On the third step, we have 0 and 0, 0 and 0 here. So the sum is going to be 1 and the carry output is going to be 0. And on the final step, we have 1 and 0. 1 here, 0 here. So our sum is going to be 1 and our carry output is going to be 0. But please pay attention that this time we are starting from LSB, so least significant bit, going through the MSB from left to right. So we have to change the order of this number to see better. So it will be 1, 1, 1, and 0 as the sum. And our carry is equal to 0. So the result of this addition is 1, 1, 1, and 0, which is equal to 14 in decimals. Now let's quickly take a look at the Verilog code for this 4-bit full adder. You can see that we are defining our module this time as full add 4, and we are again giving the port list in brackets. Then we define our sum value, which is a 4-element vector, because we are adding two 4-bit numbers. And our output is going to be carry output, and our inputs will be two 4-bit numbers A and B, and we will have a carry input as well. And in between, we are going to have wires for C1, C2, and C3, which are defined here. Then we are going to be instantiating the full adder, 1-bit full adder code that we just wrote. So we are going to say full add, and we are going to name one of them as FA0, which can be seen here. And we are going to give the inputs and outputs for that. And we will do the same for the remaining 3 full adders right here. And then we will be ending our module with the end module command. Now let's see the simulation code for this 4-bit full adder. Here you can see that we are defining this module as test bench, and we are giving A and B inputs as registers, also carry input as a register. We are defining the output sum as a wire, and also the carry output as a wire. And then again we are instantiating this time our top level module, which is full add 4, with the name FA_4, and we are giving the port list. And with the initial begin, we say that we are going to monitor A, B, carry input, carry output, and sum. And first we give them the initial values as decimal 0 to A, decimal 0 to B, and binary 0 to carry input. Then after 5 units of delay, we are going to set A as decimal 3 and B as decimal 4. Then we are going to change it to decimal 2, decimal 5, decimal 9, decimal 9, decimal 10, decimal 15. And on the last step, we are going to define A as decimal 10, B as decimal 5, and carry input as binary 1. Then we are going to end our module. Now I'm going to create a new project for the 4-bit full adder. I'm going to click on next, and I'm going to name it 4-bit full adder. I will click on next for the constraints as well. I will choose our BASYS3 board, which is this one, and I will click on finish. I will click on design sources, right click, add sources, add or create design sources. Next, I will click on create file. I will name it full add 4. Okay, and finish. I will click on OK again. Yes. And then I'm going to double click on the file and expand it. What I'm going to do is I'm going to just go to our presentation. This was our code, so let's copy that and let's paste it here. Okay, there we have it. Let's do some small modifications. Let's save it. You can see that there are some modules that are instantiated FA0 to FA3. However, we haven't defined the full add yet, so let's do that. Click on Design Sources, Add Sources. Yeah, next, create file, and this time let's name it full add. Click on OK. Click on Finish. And let's click on OK again. So you can see that we no longer have the question marks here. What I'm going to do is again copy and paste the code. I'm going to get this code and I'm going to add it right here, and I will click on Save. I'm going to double click on Full Add and I'm going to paste the code here and save it. So we can see that we have 4 instances of the full add module under our top module full add 4. Now let's click on Run Synthesis. Let's click on OK. You see that it's saying running synthesis design. As synthesis successfully completed, let's click on Cancel. We want to run implementation now. And now let's create our simulation source. Let's right click, Add Sources, Add or Create Simulation Source. Next, create file. Let's name it Test Bench. Click on OK, click on Finish. Click on OK. Yes. Now we have our test bench here. Again, we are going to copy and paste the section. Let's copy this section and paste it here. Okay, these should be replaced with semicolons. And our test bench is our top module now. So let's click on Run Simulation to see what happens. Okay, let's see our TCL console. You can see that for A is equal to 0, B is equal to 0, and carry in is equal to 0. These are our outputs. Carry output is 0, sum is 0. And for A is equal to 1 decimal 3 and B is equal to 4, our sum is 7. And for A is equal to 00100101, our sum is also 7 in decimal. When we are adding decimal 9 with decimal 9, you can see that we have a carry output and 2 as the sum. So this makes 16 plus 2, 18. And 10 plus 15, we have a carry output and the sum is 9. And when A is equal to 10 and B is equal to 5, and if we have a carry input as 1, then we will have carry output as 1 and sum as 0, because our result is going to be 16 in decimals. And if we zoom in to this section, you can see easily that for A is equal to 0 and B is equal to 0, sum is 0. For 3 and 4, it's 7. For 2 and 5, it's again 7. For 9 and 9, the sum is 2, and our carry output is 1. And here we have A as A, which is 10, and we have F for B, and the sum is 9, and we have a carry output. Now that we have done our simulation on Vivado and saw that the results are okay, now it's time to do the implementation on our FPGA board BASYS3. So what we have to do is we have to select which inputs we will have and which outputs we will have. So the inputs that we have is a 4-bit number A and also another 4-bit number B, and as an input we have another carry input, and our outputs will be the sum and carry output. For inputting our number A, let's use these 4 slide switches starting from switch 0 to switch 3. For number B, let's use these 4 slide switches which are from switch 8 to switch 11, and let's use this final switch 15 for the carry input. If you want to have the indices, this one is going to be B and this one will be B0, B1, B2 and B3, and this one is going to be A and this one will be A0, A1, A2 and A3. For the sum output, let's use this 4 LEDs, LED 0 to LED 3, so this will be our sum. Let's leave a blank LED, and after that let's use LED 05 for the carry output. Now let's modify our XTC file accordingly. So now on the left hand side we can see the master XTC file for our BASYS3 board, and on the right hand side we have our full adder design source file. What we are going to do is actually very easy. We are going to change the inputs with the related switches, and we are going to change the outputs with the related LEDs. So we remember that the switch 0 to switch 3 is going to be our input A, so we can directly change this. Let's find switch and let's change it with A. Until the end of switch 3, that's okay. And remember that for input B, we were using the switches from 8 to 11, so we are going to replace it accordingly. So we will write B0 here. This one is going to be B1. B2. And B3. And our final input was the carry input, which is going to be at switch 15. So this is going to be C underscore in. Okay, now we are done with the inputs, and our outputs are going to be sum from LED 0 to LED 3. This will be sum. We can find and replace. Oops, we should delete the last one. Okay, and we were leaving one LED blank, and then we were showing the carry output on LED 5. We should delete these comments. For input A and also for input B, we should delete. And for the carry input, should delete this one. LEDs are okay. And this file seems fine. So let's copy that. Let's go to the Sources tab and let's click on Constraints. Right click, Add Sources, Add or Create Constraints. Next, Create File. Let's put this BASYS3 constraints. Okay, and finish. And we can directly paste the file that we modified to here. Actually, there are many things that we don't need, so we can delete them as well. Things that we don't use. You can see that they are already commented out, and we can delete them. And we are not using anything other than slide switches and LEDs, so we can delete all of this rest. Now we have a more compact XDC file. Okay, now let's click on Run Implementation. So let's click on OK to do the synthesis once again and save for sure. And click on OK. It's running synthesis design. Okay, it says synthesis complete and saying initializing design. Okay, now let's click on cancel. And now let's connect our BASYS3 board to our laptop. And let's switch it on. Okay, let's click on Open Hardware Manager, Open Target, Auto Connect. Okay, you can see the Hardware Manager here. Let's click on Generate Bitstream. Click on OK. You see that it's saying running right bitstream. Let's see the log for the problem. Okay, I guess we have a problem right here, so we needed to have this LED5 replaced with carry out as well. And let's delete this LED4 and let's delete these unused LEDs as well. Let's save it again. Let's run synthesis once again. Synthesis complete, and let's run implementation. Okay, it says implementation complete, and let's click on generate bitstream. Okay, now this time it says write bitstream complete. Let's click on cancel. Let's click on program device. Let's choose our device. And let's click on program. Assuming that the device is now programmed, let's try to do some changes to the switches. So you can see that when I turn on this first switch, I get a sum of 1, which is what I expected. So let's see if it's, yeah, okay. We can see that A0, A1, A2, and A3 are working. So let's do this. Let's have starting from switch 8. If I turn switch 8 on, I'm expecting the sum to be 2. Yes, perfect. Let me check if you can see it. Yes. So we have 1 plus 1. So let's make it 3 plus 1. You can see that, yes, the result is 4. And for example, let's make it 3 plus 3, and our result is 6. You can see on the LEDs. If I increase B, and you can see that we have 7 here, and we have 3 here, so the result is 10. You can see it on the LEDs, 8 plus 2. Let's add the carry input, which was this switch. So I added 1 to it, so you can see that sum is now 11. So let's delete all of them. And let's again, for example, this one is 8, and let's 8 plus 8. Yeah, perfect. You can see that we have carry and the sum is 0. So if I add 4 to B, so it's going to be 12. You can see the result here. And you can see that our board is programmed and working perfectly. This was the end of the video. I hope it's been useful for you. If you have any questions or comments, please write them in the comment section. Thank you for watching, and see you in another video.